So I remain Jarrett Dunn from yesterday, still the same person. So one of the reasons I'm up here talking about suspensions, I've been doing this for a long time. I actually got into solar car racing through normal racing. I'm originally from Spartanburg, South Carolina, and if those of you who are not Southern rednecks, Spartanburg, South Carolina is the home of NASCAR racing. So I grew up from the time I was about 5 in NASCAR racing shops, doing performance. I continued doing that through high school, college. That's actually why I went to Georgia Tech as mechanical engineering, was to do race cars, did Formula SAE before I got into solar car. I continued doing this. I actually have a side business doing suspension setup for race teams. I worked through college, worked for a guy named Joseph Conrad who has a Porsche team. He runs out of Atlanta. Very good team, lots of fun, but spent a lot of time doing this. So I have a lot of background in suspension design and setup. Okay, so again, we're going to have the introduction. I just introduce myself. We'll talk about a couple of the suspension types. We're primarily going to talk about front suspensions. Rear suspensions, if you go with a four-wheel drive car, or four-wheel car, not four-wheel drive car, a lot of them are very the same from the front to the rear. Probably 90% of our teams use a trailing arm and a center line wheel in the back, so not very interesting, not as much to talk about. Talk about some of the key terms. We're going to talk about how you measure your alignment. This has been an issue a lot in recent years. We've seen a lot of interesting things happen with this. And this is really critical to your car running efficiently and not blowing tires out. We're also going to talk about Ackerman steering, which is one of the problems we have a lot with is Station 3, the tilt and turn. The turn test, which is interesting. I'll tell you a quick story about my team when we get to that one. And finally, some of the best practices. Okay, so common suspension types. The first one over there on the right, double A-arm suspension. That is probably the most popular suspension type we see. Very nice suspension. Gives you a lot of adjustability, a lot of flexibility in how you do it. On the left, we have a McPherson strut. This is the most popular in your production car. The problem is it's very hard to design one. It involves a lot of custom machining. So really your only option for it is to go out and buy one. Well, most of these are designed for production cars, and what might be appropriate for a Ford Escort doesn't really work very well for a solar car. So these tend to be very heavy. There's also not a lot of ways you can adjust them, so you're pretty much set with how the Ford or whoever you got your car from worked. We have seen some that for smaller cars worked very effectively, but how you install this is very important, because once you bolt it on, you're not changing it. Whereas with the double A-arm, you have rod ends. If you don't like it, you can take it off, unscrew the rod end a little bit, screw it back in, and you have a lot of adjustment in it. Another one we see very commonly is the solid front axle. These tend to be kind of heavy. We see a lot of trailer axles that are modified, but it's very strong, very simple. This is probably the most simple suspension that we have. Oh, and my animations are out of order. Some of the less common ones we see are torsion axles. Basically, you use the twisting of the axle as the method for providing suspension. You also have radius arms. If anyone familiar with hot rods, basically goes back. It's kind of like an A-arm, except the arms go back instead of to the side. And we have mountain bike suspensions. Several teams attempt to use mountain bike suspensions, your double A-arm or your double things go to forks. I highly recommend against doing it. As William talked about with the suspension or the wheels design, they're not meant to be loaded in sideways, so as you turn, you put a lot of load on them, they tend to fail. Okay, so I think vocabulary. So toe is the angle, basically of the wheels, how far they are from parallel to each other. Caster is the angular displacement of the steering from the vertical axis. Camber, the angle of the wheels with respect to the vertical axis. And scrub radius, the distance between the steering angle, or the intersects of the ground, and the contact patch of the tire. I'm sure everyone's perfectly clear on that. Words are great. Everyone loves reading words, has perfect understanding. So pictures help a lot with this. Oh, and contact patch. So contact patch is kind of important to you. The contact patch is where your tire touches the road. And it's probably the most critical thing in your suspension. And steering axis, the line between the pivot point and the top of and the 2 points of the wheel. Okay, so this is our picture of top down looking at a double A-arm suspension. So we have the center line of the car is the red line that goes up and down, and then you can see down the big arrow pointing the front of your car is down. So this would be a toe-in situation. As you can see, you have the center line of your car, your wheel is pointed in, and the angle of your toe is the distance between the center line and the actual angle of the tire. And so the opposite of toe in is toe out. Well, basically, you're pushing your wheels along sideways, so basically, if you've ever walked or pigeon-footed, so your feet are pointing out as you go down the road. So now we go back to camber. Camber, the vertical alignment of your wheels. So you see, you have vertical. This one's got negative camber, so the wheel is tilted in. And the opposite of that is, of course, negative. Wheels pointed out. So camber or caster. Caster is how far it's pointed back. So this is kind of looking from the inside of your solar car, looking out at it. If you were sitting in the driver's seat, imagine sitting in the driver's seat and looking out to the left of your wheel. That's positive. Okay. And so scrub radius, the distance between, I talked about the turn radius, so your 2 points here, for this one and this one. That's the radius that your wheel is going to turn around, your 2 points where you connect. You extend that line down to the ground, and that creates your angle, and you connect your wheel. So the reason this one is important is how much force it's going to take to put your car, and how much wear and resistance you're going to have in turning. There's a real simple example of this to demonstrate this. If you have a cup or something in front of you, you pick a point and put it on your cup on a point. Then try to turn it. It's not a lot of resistance in turning. Now, take your arm, put your elbow on that point, and move your cup out and drag it around the table. Now you have this big radius where your cup is moving. So all that movement that you're doing doesn't actually buy you anything as you're turning, but it's all energy that you have to expend that's not adding to your turn. It's also dragging your tire across the pavement, so you're adding wear to your tires. So, the reason we're concerned about toe is toe affects how much wear your tires get. If your wheels want to run straight down the road, if they're turned out or turned in, you're actually dragging the tire across the road as you drive. So that adds wear. Your normal car has about a degree of toe in. Race cars may have 2 or 3 degrees. This really affects your ability to turning. Having toe in makes your car want to turn. It makes it much easier. A normal car has lots of tire. You're never going to see the effects of toe on your normal car unless you have really excessive amounts, and then you'll see excessive wear. The problem with solar cars is we like to use really thin, really lightweight tires for efficiency. So if you're dragging the tire and having excess wear on it, your tires will wear out. The Bridgestone Ecopia tires were the default solar car tire for about 20 years. And they're still amazing tires. However, they are incredibly thin. They have a little tiny bead right in the very center, and if you're not exactly on it, they wear out very fast. And even if you're very good at changing your tire, say it takes you 5 or 10 minutes to change a tire, that really adds up if you're changing a tire every 35 minutes or 45 minutes. I've been there. I don't recommend it. It's not a lot of fun. And if you're not as efficient as my team wasn't, when it takes 30 to 40 minutes to fight one of those tires onto the rim, you can lose a lot of your day as you're trying to mount tires and change tires. So toe in or toe out greatly responds to towing response. Toe in provides stability. So if you have a lot of toe out, your car is going to want to be jerky, but it'll really turn. If you have toe in, your car is going to be very stable. It's going to want to go in a straight line. Camber is going to affect the grip and stability and cornering. So thankfully, we don't do a lot of high-speed cornering in solar car racing. Even on the track, we have nice wide turns and they're very short. So camber is not really an issue for solar cars. So my recommendation to you is don't have any. Have your wheels go straight up and down, which is nice. Not really up. And so the one thing with camber is if you have a AA arm suspension, you have this thing called camber gain. As your suspension travels, if your A-arms aren't the same length, geometry gets involved, and geometry is annoying. Nobody likes geometry. But as your suspension travels, your camber changes, and sometimes it can be very extreme. and you get strange things. And that can create wear on the side of your tires. It can also change your handling as you're driving. So as your car, if you hit a bump, your car can all of a sudden want to do strange things and jump to one side or the other. Caster creates straight line stability, provides steering feedback, makes cars harder to turn. Negative makes the car unstable. So always recommend being positive in this. So just gave the quick definitions of the terms. So there are no right answers for this. It's all a balance of how you want to drive your car. As I said, I worked for John Conrad I've actually still worked for him. So I've worked for him for 25 years now. He has a Porsche race team. He's actually a neurosurgeon in Atlanta, very good. Decided he wanted to go out and buy race cars, his midlife crisis. Turns out he was really good at it. So then he went out and bought another one, and his son races. So I've been doing his setup for 25 years. There are generally accepted standards of how you set up a Porsche. You do about 2 degrees of toe in, certain balance, certain characteristics. But that's not necessarily a universal experience. His son sets up the car completely wrong. And I've tried multiple times to set the car up the way in sort of what's considered correct. However, for him, it doesn't work. For some reason, he likes to have lots of toe out, and his car is twitchy. Nobody else can drive it. But that's how he is the fastest in his car. So we set up his car up completely wrong. I can't drive it. I can drive the main car. I can't drive the second. So you set your car up however works for you. And I talked about in the telemetry testing, the only way to know how to set up your car and what works to be efficient for your drivers is to test the car. And that's why when you design your suspension, you should design with some adjustability so that you can figure out what works for you. And if you're having problems, going back to the references. So I think that's... Okay. Oh, well, I'll get to the reference in a minute. So this is one of the ones we've seen quite a few times. Most teams want to have 1 degree or less of toe. I recommend having 0 toe, but that's a decision that you have to make. But when you measure toe, repeatability is very important. So multiple ways to measure toe. The easiest way is to take 2 sticks, straight sticks, and put them against your tire. Measure out, just have them go out forward of your car, and then pick 2 points further down the car and measure the distance between them. This one has a lot of animation in it, so. Okay, so measure A, measure B, measure C. If you know the distance C, because you should mark these, use the same points every time. A little bit of geometry. You can find out what the angle is. The angle itself is not actually all that important, so long as you know what you want. So you're looking at having a consistent distance. If you do it the same way every time, the actual angle isn't as important so long as actually measuring it. So if you find that you have a 1/4 inch, that's perfectly valid as saying that I want 1 degree of toe, just so that you can repeat it every time. So one of the things we've seen, geometry. If you measure at different points, you have different lengths. We had the ones I had earlier. So if we measure this way one time and this way another time, those lines are different lengths. So you won't get the same thing. And I watched a team 2 years ago do this, and they were trying to set a certain degree of toe, and they measured it once. It was one way. They adjusted it a little bit. They measured it again. It was completely different. I made adjustment the other way, measured it, and used different points. And I watched them for about 45 minutes try to get that toe dialed in as they were going back and forth, and the team was getting frustrated, and they were yelling at each other, and it just wasn't a good scene. And they got tired and hot and couldn't convince them that they were measuring different places, and it really doesn't matter. Okay. Another way to do it is if you have PVC or some other kind of thing, if you have straight lines and you measure a distance between them, have 2 straight things that you know are parallel, and just measure the distance from those parallel items to your wheels. So you measure A, measure B, you know C, cosine distance. And so the cars I work on average between $150,000 and $200,000. And when I'm at the track, this is how I set up suspension with 3 pieces of PVC in a loop and 2 straight strings that I know that they're parallel to each other. So this really does work quite simple. Okay, Ackerman steering. Station 3 has historically been one of our most notorious stations, people not being able to conduct the turn test. 1999, we built a car, we could not turn. We did all the things that we told you as workshop not to do. We finished the car in the parking lot actually during scrutineering. So we were at Station 3. We could turn one way, so we did one way, then we went in, distracted the judge for a little while, adjusted the steering arms, and we were able to turn the other way. They know that now, so you can't get away with it. But the way you do it is you have the center of your turn, the point you want to turn around. You might need to know how far that is from the outside edge of your car. You might find that in the rules, and I can't remember them off the top of my head what section it is, but what? 15 meters? That's diameter or radius? That's diameter. So 7.5 meters from the outside of your tire over here to your turn point. You're going to have a circle that goes 15 meters in diameter, 7.5 meters in radius. So the idea is that you want your tires to actually roll continuously around that. So your back tires are going to roll in a circle or in a straight line. Your front tires have to travel in different radiuses, and you want to travel around a parallel circle to it. So they're going to have to turn different angles. Otherwise, you're going to push your car around instead of turn. And my lines do not show up. So the way you do it is, if you have your steering, you want to draw a line from the center of your rear axle to the steering axis of your front radius. You draw a straight line between those points. You want your steering points, your steering arm connections to be on that line. And then you want them far enough back that you have the leverage to be able to turn. Okay, so the best practice with suspension, or with steering, is to be consistent. Every time you do it, you want to do it the same way. Same people if you want to be preference. We saw in the video Houston, Mississippi, one for a lot of years. They have the same people do it every time. The same person checks the tire pressure. Same person checks the suspension setup, and they do it every time the same way. It is amazingly efficient how quickly they can do it and how repeatably they can do it. And it is one of their keys to success. Make dedicated tools, mark them, take care of them, know where they are. As I said earlier, suspension is all about efficiency. We're not looking for a high-performance suspension that can allow you to corner at high speeds. Everything you do is focused on efficiency in this. Okay, and so with all things, the references are important. So this one, Tuned to Win by Carol Smith, is an incredibly dated book, 1970 published. Really good, really easy to understand on suspension, on all the trade-offs and all the things we talked about. Available for like $20 on Amazon. The Winning Solar Car. This is my favorite book in the world. It's kind of the Bible for solar car racing. It is, every solar car team I think should have this on their bookshelf somewhere. Has a lot of math in it. A lot of it's not necessary, and some of the information is a little bit dated. They still talk about potassium batteries, which I don't think anyone has used in 15 years. But suspension geometry, aerodynamics, and a lot of those topics haven't changed, so I highly recommend finding this particular book. And again, it talks a lot about the trade-offs and a lot about the engineering of suspension design and steering. And with that, I will return it to William. Does anyone have any questions, I guess, first? Yes. What?
Any more recent books that we could reference?
I am not sure. Those are the ones I've used for years, and I'm sure they're out there if you wanted to go look for them. But
yeah, I'm not familiar with any new books as well, but these books that are there are still relevant today. I mean, not sure.
yes.
You mentioned how important it is to test run in, and I know there's a requirement there, and this may be for later in the presentation, but any best practices for testing, where to, I'm from this area,
Well, for this particular one, any parking lot will work. Pretty much every high school I've been in has a big parking lot somewhere, and not a lot of people in it Saturday afternoon, so it's a good, safe place you're not going to run in. For some of the track, a lot of places have tracks. Some schools won't let you run on their running track, but we've had a lot of schools to test on their running track, good quarter-mile loops. Yes.
In the past, I used like the Mexican Mall, they had like a mile and a quarter loop, and before they opened every Saturday, Sunday, we went there for a few hours to test the machine. They were really helpful in letting us do that, so we could have a bigger truck, because our high school parking lot is relatively big, but curbs weren't our friend, so that wasn't a problem, it was really helpful. And testing our shape vehicles as well with it.
That's a really good idea.
Oh, and UNT, they let us test in their parking lot as well.
Another option is like a local go-kart place. You can go and ask the manager if they'd allow you to run beforehand and put their name on the side of your car as a sponsor. And they don't really have to do anything other than let you in an hour early, run around, and we have a nice little track to test on too.
Okay. Any other questions? In the back. The two books. The book is called The Winning Solar Car, and you can occasionally find it on Amazon. It's out of published, but it's, I think, $23. SAE, Society of Automotive Engineers. You can get a PDF copy for $23, I believe. I'm old-fashioned. I actually like books, so I bought mine on eBay.
You can still get the speed of light in Australia in 1996, and that mentions Doc's team. Speed of light. It's still available in Australia.
Speed of Light's another good book. Another one I didn't mention. It tends to be more. It does cover suspension, but The Leading Edge is written by the MIT advisor. If you can get past reading the math, he's an MIT professor. It can be dense, but he's got a lot of good information in that book also.
Is that the same book as the aerodynamics of slow-moving land vehicles?
Nope, that is yet another book.
Oh, okay.
That one's really, I didn't even list that one because that one is incredibly dense. And if you're not an aerodynamics engineer, I mean, that's really meant for aeronautical engineers, but also a good book.